My name is Antonio Pastor. I'm working on Telefonica in the research area of the company. I'm happy here to come here to present you the activity what Telefonica has been doing in the recent years about disruptive technology very related with the photonic network, that is the quantum key distribution. So I'm not aware about the knowledge the audience have about this technology. So I've decided to make a brief introduction about this technology just to give some perspective of what is this QKD and why it's important for telcos, and this is the reason why we're working on it. So let me present you first the topics we want to discuss. One is precisely what is quantum key distribution, where this come, and why it's important, or why telcos like Telefonica have interest in. The second, I would like to present more or less the experience we've been working with this technology and what we have been doing in file trials with real networks. And the last is just to introduce you what are our plans on this technology and what we expect to make in future. So the first, just introduce the concept of quantum information. That is basically the idea of if we want to use quantum mechanics and the properties that it has for computing, that is some like a research area that has been leveraged a lot of interest, basically because have some properties that allow you to increase the compute capacity. But in our case, we are not focused on computing, but on security and cryptography. But the principles are the same. So we are searching for something that can allow you to make 0-1 like any kind of computing. And for that, we use physical capacities offered by quantum mechanics and to represent zeros and one. That is, in the quantum representation is made by this get 0-1. And physically, it can be implemented different ways, starting from photon polarization, controlling some particle spin state, or entanglement of different particles and how the energy level change. There are different technologies available, and probably will be arise more in the future. But all these solutions, what expect is to support these quantum mechanics principles like superposition and non-cloning. The idea is basically that you represent a qubit, that is the unit base for this representation, as a superposition of different states. And only when you measure this qubit, you will consolidate in one state, 0 or 1, with a different probability. And only when you read it. So meanwhile, you can have both states, and for computing is very interesting. But as I mentioned before, we are more interested on cryptography and security. And this means that we can leverage these properties to allow to apply this called the non-cloning theorem. That the idea is that once you read a qubit, you cannot clone the information, you cannot copy the information, and if someone reads a photon, change the state. This, from the point of view of security, is intuitive, that can be helped to protect some kind of communication. So the difficult part is how to design a solution that allow you to leverage these physical principles. And for that, from 1983, that was the first time someone proposed a solution. We have been doing more and more steps to offer security service based on this quantum key distribution. So Bennett and Brassard described not only the theoretical use for security of quantum mechanics applying to quantum cryptography, but how they design a specific protocol called BB84 that allow you precisely to do a solution to share keys over a quantum channel with 100% of security. This has been evolved. There have been other versions like E91, and recently in the last year, and this is the technology we've been testing, is the one what is called continuous variables. That is more robust, as we see a bit later. But at the end, as you can see, there have been some evolutions about this technology. Starting for 1819, where it was the first lab tries to commercial products that are available today. And we have been testing that, and we expect to see more and more in the following years. So just to understand what is quantum key distribution, if you can see in this picture, basically, this is the classical diagram related to security when you have Alice and Bob and you want to make a secure channel to communicate between them, and you always have Eve, that is the eavesdropper that always want to read the message that they exchange. And the idea is to set up a couple of QKD systems or devices that are connected with two channels. One that is called quantum channel, another that is a public classical channel of data, both of them using photonic fiber for connecting them. The public one is based on classic technologies, and what is more important is authenticated and with integrity capacity. I mean, if it will be not able to modify the content of this channel, but it's not encrypted, it's public, so if in any moment can see what is moving around this channel. And the idea is that based on the magic of quantum key distribution, you will produce a couple of keys, the same key on both ends, securely, that can be used by Alice and Bob to encrypt messages between them. This is a very, very basic schematic of the first protocol that was invented, the BBB84. In this case, as I mentioned, the qubits are based on photon polarization. So the idea is you use I don't know if I can make a pointer with it. Yes. So you have a laser that has been modified to produce a very, very weak light, in the sense that we expect to send only one photon at a time of light. And we can use two bases of polarization filters, basically what is called rectilinear, vertical, horizontal, or diagonal. And you code 0, 1 based on this scheme. On the other side, Bob just will have these filters to read the photons. And the principle here is that if Alice sends a photon using one base, polaris base, that is not the same, if it is the same, of course, he will detect the 0, 1 based on the same polarization. But if Alice decides to use another one, different, that the one is selected by Bob to read, it will have, by this 40 degrees shifting, it will have a 50% to detect or not the photon. And here is where the quantum mechanics applies. So the idea is that Alice chooses a random sequence of bits and send it. Also select randomly the base he will use, rectilinear or diagonal, and send the photons. On the other side, Bob probably he will choose also randomly the base he will read. When the bases will be the same, he will be able to read 1 or 0 depending on the case that will fit. But if he uses the wrong base, he has a 50% to read the wrong or the correct photon and the polarization to read the value. What Bob made after receiving all the information is to send back using the public channel the base he have choose in each time, and Alice responds saying which one are the good ones bases that he have used in order to have this set of 0, 1 that are correct. This is the base that later is post-processed using technologies and post-processing like privacy amplification and so on that allow you to have a string of keys that is secure in both terms and can be used for security service. So the question is why this is so interesting or why it is so valuable for telcos and in general for anyone who want to produce a security service. Basically because quantum key distribution is what is called information theoretical secure. I mean, it can be mathematically proven that no one can be able to break the key or to read the information of this key when you apply this protocol. And this is protected by the law of the physics. We will have to redesign the concept that we have of the universe if we will be able to break these protocols. And also this means for telcos that this technology can allow you to extend your concept of the physical security. Today a telco expects that the physical building and the physical equipment they have are secure physical places when they have some kind of trust when they deploy and implement security service. Using this quantum key channel allow you to extend between two places this physical security level. So the idea is to work, maybe it's a disadvantage that this technology today is only ITS for symmetric keys. I mean, only for algorithms and for cryptography that allow you symmetric key exchange, not for asymmetric. But it can be combined with other existing key exchange technologies like the public key cryptography, that's asymmetric cryptography, to use it jointly. But after that, it has another property that's very interesting for, in general, for anyone who wants to provide security is that being IDS, it can be demonstrated that no one having any kind of computer capacity will be able to de-encrypt or to read the content of an encrypted communication or encrypted information. Because this, as I mentioned, is ITS. So these recent concerns about post-quantum computing that will be break all the existing or previous existing cryptography algorithms that we are using today, like RSA and similar, that when we have a computational capacity of a quantum computer, we will be able to break. This don't apply to this. This will be secure after availability of the quantum computing. This is the reason that can be presented as an alternative to post-quantum cryptography that is starting to develop today. So then why is this not widely used today, the quantum key distribution as a solution? Basically because it's a difficult technology. When I say it's difficult technology, I say that it's a very weak signals. As I mentioned, for example, we have to send one photon at a time. So the energy is very, very weak compared with traditional communication channel. It's very dependent of the noise. And also the distance decreases very, very high at some point, the key read rate that you can produce on the system. Of course, this is improving with the time and with technology, but it's very, very, at the end, you can have the idea that it's a very delicate technology. It has evolved, but still delicate. So the last versions or the last approach is what we call the continuous variable. That basically, instead of work with single photons, use the quadrature for the electric field of electromagnetic waves that have very similar principles of this superposition and non-cloning. This last technology have a lot of advantage. That, for example, you can use a standard homodyne or heterodyne detection solution sensor that is very, very more cheaper than the single photon detector. Can live together with classical channels because at the end have some behavior like a noise filter. So it's very, or it's more promising in the sense that can be industrialized, miniaturized, and can have cheaper device on the market. And as the disadvantage or the cons of this technology, as I mentioned, is that have more, I would say, is less tolerant to losses on real networks, I mean, on the real fiber. So the discrete variable, that is the technology that based on one photon at a time has been improved to be better for the distance and the losses on the fiber. This technology still is a bit behind of that, but we expect that in the future can be improved. And also is very, very heavy computationally in the sense that it have a lot of more post-processing on the data, raw data, to generate the keys. So what we've been doing in Telefonica on this activity in the recent years. So basically, since we started to work on this at the beginning of the 2000s, we start to evaluate what was in the lab. We contacted with universities to have the knowledge. And after that, we have started a deep collaboration, for example, with the UPN, that is the Center of Computation Simulation in Madrid. And we start to set up some trials, labs to evaluate what is happening on the technology, and if it is realistic to use. Indeed, not only we discovered that, we were able to, for example, to generate some patents in collaboration with the university about this technology. And we make two main testing, one in 2009, and this last summer on 2008. The first one basically was to test this first based on BB84 protocol that was indeed use a commercial QKD device that is produced by ED Quantique, that is the company, the Clavith is also. We set up a lab using commercial and standard devices on Telefonica network on that year to evaluate how this technology can be used. And well, at the end, on the lab, we were able to set up some low rate bit to generate keys, and we discovered that more or less was potentially be able to be used, but was not ready for commercial solution at the moment. The next test we have been doing, this as I mentioned last summer in 2018, was in collaboration again with the UPN, and in this case we searched a partner that was Huawei, that he was researching these quantum variable technologies, and they have several prototypes to try to solve this limitation that we found in the discrete variable solution. So apart from that, we try to join this technology with a new concept that is SDN and NSB, that is probably things here is a small slide about that. That is try to decoupling the hardware and the software on the communication technology. What it means is to offer some kind of programmatic capacity of the network using standard protocols that allow you to manage at a low level the network devices. So this is a reality today. So we are indeed have been working in several projects. Telefonica have a architecture base called Unica that try to leverage this SDN and the NFV technology to deploy technologies on deployments more easy to manage and more efficient on the networks, and the idea was to try to evaluate if it is possible to bring QKD as another enable on the network without making very difficult the deployment of this technology over the network. So this was the idea of the project. And what we made basically was we bring 3 devices, physical devices, that is in this picture, that's provided by Huawei, that is composed of a standard device, a OSN from the portfolio belonging to Huawei, a couple of servers inside, and the specific QKD boxes that was developed or integrated by Huawei. And we set up 3 links over Telefonica network. This was a production network, in 3 different buildings, and we made this connectivity to test this coexistence between quantum channels and classic channel over the same fiber. Okay, so the idea here in the picture is the summary. We have the different classical channel for moving data, and this is the one of quantum. Of course, this is how we call it a pilot reference. Indeed, the signal is very, very weak, so we use some kind of pilot to identify which channel is moving the quantum channel itself. But as you can see, it can coexist with the classical data channels for the communication. And of course, we will add some SDN capacity to manage these QKD boxes. This is the map of the Madrid city, where we have 3 buildings, the Almagro, Norte, and Concepción is the name of the building, central office that Telefonica have equipment. And we set up a standard commercial connectivity between the 3 of them. Here you can see more or less the distance and the loss of the quality of the channel, the attenuation, that was part of the idea to evaluate. In this later we made mix joining both or several of these points to make long distance to evaluate, but the idea was to connect these 3 environments. And to make that, we leverage first. The idea was to be able to test only in 3 months, to set up and make the exercise only in 3 months, to evaluate this technology. So beforehand, we worked with Huawei to setting up some APIs and tools that they provide about their boxes, so we can develop some proof of concept of services that we could develop over this technology. So when we started the project and they bring us the equipment, just we have to join the components and make the integration very quickly. Indeed, we set up our lab in Telefonica Hub in Almagro, in our future network lab. We have set up here 3 nodes connected between them and make the integration during 1 month to evaluate that everything was okay. And once that this was ready, we moved everything to the production places, and indeed we added some basic service like the streaming with some webcams of each of the nodes that they were using indeed this classical channel to send the signal and the video, and make several texts about our demo. Indeed, for example, we work with Huawei to simulate some kind of attacks injecting noise on the quantum channel to detect it and to drop the key rate. So we cannot use any key that could be vulnerable, but in this case it was successfully detected, and the solution is to stop to send keys. Meanwhile, you are not confident that the channel is secure. So these are a summary of the service on demonstration we planned and execute. The first one, the basic one, was basically use this commercial product that include from Huawei that include an encryption card, and using the quantum box, they provide the keys to these encryption cards to offer encrypted traffic in line over the fiber connected in all of the classical channels. Other advanced service that we tested, for example, was precisely how to manage the control plane on the NFV architecture. I mean, this is the orchestrator of the virtual network function that basically you can see as a virtual machines that offer security service, network service like routing, switching, and so on, running in virtual machines in different data centers. So they deploy this technology using secure channel. These keys were provided by the quantum boxes. And also we simulate a customer connectivity between different sites using a VPN based on IPsec, and this IPsec also use keys provided by the quantum key distribution channels. The final test we tested some other technologies that was in research, like this that is called order proof of transit. That the idea is to use some cryptographic algorithms like the Shamir-Sharet secret, that is a polynomial algorithm that allows you to distribute piece of keys between different nodes, because the final idea is to be able that cryptographically be sure that the traffic is moving through a specific node on the network. In this case, this specific node were the 3 nodes where we have our quantum key distribution devices, and we provide keys for this algorithm in these nodes. The last one basically was to use the idea of, if we are not able to offer a service between this node and the last node because they are really far away one from each other, so we cannot set up a direct quantum channel. We want to offer a solution that using a third intermediate node, we can interchange these keys between them. So the idea was that there was a quantum channel between this node called Bob1 and Alice, and a quantum key channel between Alice and Bob2. So they change these keys, or they set up these quantum key channels, and we share using this the keys that allow them to offer an encrypted, secure channel between the both ends. So what was the main lesson learned on that activity? Well, first, we identified that there were not any special needs for environment condition. I mean, we put the equipment in the same place. We put all the network equipment we have usually on the network. Indeed, we don't require any specific requirement about climate, noise, power. This was a key aspect because in our previous experiment, if the room temperature vary a bit, the system doesn't run. And similar problem we discovered in the discrete variables solution of QKD. This continuous variable produced by Huawei was perfect for standard equipment or standard premises that telcos has. Cost and space. So indeed, one of the key aspects of the solution was to use off-the-shelf components like laser, detectors, software-defined radio that is cheap and easy to set up. So the idea is that despite to be a big box today, it should be relatively easy to miniaturize and to produce commercial with a reasonable price in the future. The third aspect was the attenuation and the loss on the connectivities we have on our network. We discovered that, for example, when we start to set up our production system, we lost a lot of time trying to solve a problem that basically was solved. We were unable to make this quantum channel to be set up. And after working a bit on the problem, we discovered that just was a question of dust. So we have to go to the place and clean a bit the fibers. And what in another situation for classical communication is acceptable, the quality of the cleaning of the endpoints in this case was not enough. We have to make a bit effort to cleaning very well the connection to reduce the loss. And from that moment, we have a clear quantum channel running up and running. So this can be a handicap if we have to change a bit the procedures that the telco have in order to keep clean or more cleaner than usual the setup on these specific services. And well, the procedures we use, like installation, maintenance, and so on, it seemed to be very similar as we have been using. Indeed, we decided to bring, not to use specialized personnel to make the installation. We use the standard personnel that they get used to put this kind of, not this kind, any network communication device when they have to install on production site, and they are not aware about they were working with QKD system. They only know that he was moving some racks, some network devices, and we discovered that everything was smoothly running, and there was able to manage this. We have some minor problem related to the booting. For example, we have a power cut in some moments, and we have to make an order started that we are not get used on a standard communication system, but this prototype was not well set up for that. But at the end, it's a question of refining a bit the product. So we are not really concerned about that neither. And what about the future? So in the future, what we expect is to make basically 3 activities. One is to promote the standardization of these CV-QKD technologies and the integration with SDN and SV. Today, there is a strong activity on standardization in the HC related QKD, but it's more focused on the devices itself more than in the interfaces and the open access with third parties. So we want to work on that. We want to extend our quantum network. Indeed, we are trying to collaborate with research network, the National Research Network, and specifically to try to connect universities around Madrid to have more kilometers of fiber to test. And we want to promote and to push that this quantum variable QKD technology will be a reality, commercial reality on that. And how we are doing that? We have been working on what is called a flagship project of the European Union, that it is CIVIC. CIVIC is a project organized, the only project that has been accepted by the European Commission to work specifically on quantum technology. So we expect to have a long-term research on that area. There are a lot of companies. As you can see, there is a lot of interest also in other telcos, like Deutsche Telekom or Orange. This is not specific for Telefonica. Indeed, we have involved another Huawei, as you can imagine, Nokia and other vendors with strong weight on the network technology, and a lot of research companies. And the project, what expect basically is to bring this QKD technology to the telco networks. One, doing photonic integration to make it a more cost-effective solution, this quantum variable QKD, and also to be able to be more easily to integrate in telcos using this SDN technology. For example, just to finalize, this is an example of what we are expecting. So if you imagine you have your box that is a QKD system, we expect to have some kind of interfaces based on open technology, like OpenFlow, NetConf, to be controlled by SDN controller, and allow you, sorry, because here used to be an arrow, but the idea is that this raw key extraction that you use for your QKD, you can use on what is called a local key management system that produce the needed keys based on requirement that is defined by the controller to the application. So if you have a VPN service, or if we have any kind of the service demonstration we have shown before, we can use a standard interfaces to manage. So at the end, we can distribute these big nodes in any optical node or where we decide over the network. And that's all. I don't know if I'm in time, not very much, half an hour. So do you have any question? Okay, thanks.
Now there's time for questions.
Yeah.
Maybe a very fundamental question, something that I've never understood, so I'm glad I'm able to ask. The security relies on the laws of physics, the fact that you cannot copy a photon that is carrying a qubit, but isn't that exactly what optical amplifiers do?
Sorry,
Is copying photons not exactly what optical amplifiers do?
Well, the idea is that you cannot, if you copy, because physically you cannot copy the photon. If you read this with a sensor the photon, this photon you can think in terms that is consumed by the one is read information. So the final ends in the picture we show about here.
No, I understand that you cannot do it O2E2O. You cannot detect it and then resend it.
Okay.
But using the physical mechanism of stimulated emission, you're creating exact copies of photons. The physics does that for you.
I mean, so you can copy, but the idea is that here, let me check if I have the picture. Here, suppose that if you introduce here a dropper that copy and reintroduce the photon, basically the probability of have the same results here that it's expected to be obtained with the feedback that have received from the other side will not fit.
No, but that's a matter of the protocol.
Yeah.
But the safety, the security relies on the physical impossibility of copying the qubits, and that's the part that I don't understand, because that's what
it's not easy. I have admitted for me it's also difficult to understand all the details, but at the end it means that if you have the way I have seen explain this to me sometimes is if you see this basis, if you have the correct basis on the final end, you will have a probability of 100% to detect the correct photon. If you use the ground basis, you will have a probability of 50% for the ground basis. Assuming that you randomly have half of the time one correct base and one ground base, probably you will have 75% of success to read the keys. If someone in the middle reads and reproduces, he has to select randomly what he remit to the final end. So he reduced the probability to a random to 50%. So here, this displacement of the percentage is what Alice can detect with the retrofit information from the classical channel to identify that something is wrong, and it's not feasible to. You will not need confidence on this key exchange. So you have to drop this and start again. So this is the basic idea.
Probably worth a deeper philosophical discussion. But
yeah, probably you have to take the reference of the paper to read it in deep, because for me it's not easy either. Okay. I have to admit of that.
Thank you.
Okay.
Thank you. Any other question? No question? I have one myself. Okay. You showed in your SDN trials scenario in which you were generating the keys with quantum technology, and then you were feeding these keys into regular IP network and services like SSH and such. So once you feed that key into such a service, does it become vulnerable as well as other keys generated in regular algorithms?
Of course. I was the myth, of course. So the idea is that it's related with this physical security what I mentioned before. So if you are in your premises building, you put these boxes and you execute these classical algorithms and this classical service over this node, you expect to be secure on that point. So once it's moving outside is when the insecurity appears. So we assume that, and with what currently we are doing today, when we offer classical based on VPNs or other security service, we assume that physically no one is going to be tampered inside of the device. This is where is the security, I would say, fit on the network. There is no alternative for that, but the problem is once you leave the traffic on the information, leave your network, your devices or your premises, then, for example, when you go through internet, then there is where is the vulnerability. And here, when we expect that combining these classical keys with this quantum, you will leverage to be not easy to be broken.
Okay, thank you. Any question? If not, let's thank the speaker again.
Okay, thank you.